we are decreasing the angle of incidence, and to see what will happen. Please, are you with me?
Yes, please.
Okay.
Yes, please.
So the refractive index of 1 times the sine of the angle of incidence in it, which is 50, must be equal to the refractive index of 2 times the sine of the angle of refraction, which we don't know. Okay, we just even saw that no, if we decrease theta, the angle of incidence will also decrease. But let's even behave as if we don't know and find it. So because the refractive index of 1 is 1.6 times sine of 50 is equal to refractive index of 2, 1.8 times sine of we don't know. Please help me get sine of r. Then you find r for me. Let's hurry up. Time. So sine 50 times 1.6. Which is this times 1.6. This is it, divided by 1.8. But then when we take the sine inverse of our answer, we have r. R is approximately 43. Is that what you got? Did you get 43?
Yes, please.
So as we decrease theta, what is happening to the angle of refraction in it? It's also decreasing, because before it was 46, now it's 43. Now, don't forget, this angle of refraction would also be the same as this angle of refraction, this angle of incidence. So N2 times sine of 43 must be equal to N3 times sine of this angle over here. Now we are decreasing it. We don't think it will still be 90. So let's assume we don't know. Okay, represented by maybe P. Just so as to differentiate R from the other one, P. So N2 is 1.8 times sine of 43 is equal to N3, which is 1.3 times sine of P. Please quickly help me get the value of P. What do you think will be P?
$70.
70. So before it was 90 over here. Now when you measure, it is less than 90, 70. Do we have refracted ray in medium 3?
Yes, please.
Yes, please.
We are decreasing it. So let's consider a last drop in I to be very sure of what we have. So if theta now is 40 degrees, we have N1 1.6 times sine of 40 is equal to 1.8 times sine r. R we don't know. We want to see if r will still decrease. Find r for me. Help me get the value of r when theta has decreased further to 40. Please, let's not delay.
$35.
45.
35.
Oh, I can't hear you.
35 degrees.
Oh, Gloria, your line is breaking. Please, somebody to
35.
confirm. Okay, 35.
35.
Okay, thank you. So is the angle of refraction here decreasing?
Yes, please.
Before it was 43. Okay, let's see what will happen to the other side too. So then 1.8 times sine of 35 is equal to 1.3 times sine of, I don't know, P. We don't know what will happen. Let's find P.
$52 degrees.
Come again.
52 degrees.
5.2.
Yes, please.
Okay. Before we got 70. Now it's P is 52. When we measure, do we have refracted ray in medium 3?
Yes, please.
Yes.
No. You see how you've made me suffer. Adwa,
Mr. Edia, please understand.
well, okay, so that's it. If the explanation will not help you, that the mathematics, okay, seem to have convinced you. All right. Do I clean the board?
Cedra, please wait.
Okay.
These are done.
Hello. Okay. Okay, so we're looking at formation of images. Formation of images, and we even finished that. But one of you sent me a question, and I'll use that to just explain so we can move on. When we in convex lens, when the object is placed at the center, at the focal point of the lens, what happens? So let's draw the principal axis. The markers in the system this time, in fact, it's serious. How can I buy a brand new marker and then be disappointed as if it's an old marker? Oh. This one won't even open up for me to use. So this is my lens is here. Just a very small aperture. Nanadu, are you there?
Yes, please.
This is the optical center. Let's assume a focal length. I'm assuming that the focal length is not something so huge, but I'll take about 10 centimeters. So this is 30, 40 is here. This is the 20 is here. Okay, essential measurement. So if this 20, then 10 from the other end will give me the center of curvature. Okay, I'm only considering the essential measurement. So this is F. This is another F because this is a by 2F or the center of curvature. Another 2F. When we place the object between optical center and F, we saw that a virtual image is formed. Now we want to place the object at F and use ray diagram to describe the nature of the image that will be formed. So a ray parallel to the principal axis after refraction would have to pass through the second principal focus. Then a ray through the optical center goes undeviated. When you look at the two rays in front, there is no way the two rays would ever meet. If you like, bring a long rule, let's prolong it. There's no signs of these two meeting. Now, when we prolong it at the back, this is what will happen. Let's prolong it at the back. Do you see signs of, I haven't drawn this projected line well. Whether in front or at the back, please, do you see these two rays possibly meeting one day, whether front or at the back? Do you see it?
No, please.
Good. Because they will neither meet in because they will not meet in front, it means real image can never be formed. Because they will never meet at the back, it means virtual image too will never be formed. When you have a situation where the refracted rays are parallel, we say that the image is formed at infinity. Image is formed at infinity. Okay. The image is formed at infinity. Okay. Real and inverted. Real and inverted. Somebody's question is, but where is infinity? Yes, infinity is a far place. How do we ascertain that, yes, the image is formed at infinity? This thing is based on the fact that, you see, we use astronomical telescope to view stars, the stars. I hope you are aware that we can use telescopes to view. Tele means distance, scope means view. So telescopes are for distance viewing. And so we use that to look at stars. I hope you know.
Yes, please.
Good. So if you use the telescope to view very far objects such as the star, very far objects, what happens is that because the object viewed is at a very far place, look at where the star is. Okay, using it to view, to zoom the moon closer and watch, look at where they are in space. The image of this far distance object is always zoomed and brought to the principal focus of the lens used for the telescope. So if you are using this, if this is the telescope, the objective lens of it, and you are using it to view a very far distance object, its image would always be formed over here. And when the image is formed at the principal focus, the image form is inverted. All inverted images are real. Okay, so it follows that principle that when the object is at infinity, the image is formed at the principal focus. When the object is at the principal focus, the image is formed at infinity. When we look at optical instruments, you understand better. Optical telescope is one of the optical instruments. Okay, so when you place an object at the principal focus, the image will be formed at infinity. So the image of the star's moon is zoomed and it is brought to the principal focus of the objective lens of the telescope. When you place, in the same way, when you place it here, the image has to be formed over there. A real image, which is inverted, is always formed at infinity. That is the principle on which this operates. Are we okay? Are we okay?
Yes, please.
All right. If you have any question. Now, so we have basically used ray diagram to describe the nature of the image formed. Okay. Now we can also use the lens formula, and it's the same as the mirror formula, which we learned and even proved.
Yeah.
Hello.
Please, I want to know like what how do I say? You see, we are using the ray diagram to form an image. I want to know like when, like how do I say it?
How do you say it?
You see, like you gave us the way you gave us like the rules, like you gave us when maybe a ray is like, so like I want to ask if this is also like a rule or maybe a scenario or something.
No, here you see we are looking at different positions of the object on the principal axis. Okay. I can when the object is at the optical the center of curvature, I know what kind of the image will be formed. A real image is formed, okay, inverted with the same height and size as the object, okay, and also positioned at the center of curvature at the other end. When an object is placed at the focal between the optical center and then the focal point, okay, a virtual image is formed, a virtual upright and magnified. Okay, when the object is placed behind C, behind the center of curvature, what happens? So we are looking at different positions of the object on the principal axis and the nature of the image that will be formed. And this thing must be at your fingertips, okay? At least when it is placed at 2F, you have to know. When it is placed at F, you have to know. When it is placed between C and F, you have to know. When it is placed in front of 2F, you have to know, and behind. And you can master this by practice. When you practice drawing it, you can easily master. It isn't anything that is beyond your strength. Is that okay?
Yes, please. You said different positions of the object.
On the principal axis. Okay. Different positions of the object on the principal axis. And this is peculiar only to convex, because for concave, no matter where you place the object, the nature of image will always be the same. So we don't waste our time when it comes to concave lens. But for convex, you have to understand that different positions would give you different images being formed. Please, are we okay?
Yes, please. Please, Mr. Adrian. Irene
Hello.
said she wants to ask a question, but it's like her audio is muted.
So, okay. Oh, Irene, you send the question and it's gone. Irene, you were not listening. I said the image formed, a real image which is inverted will be formed at, okay, a real image inverted, okay, inverted and magnified, a real image inverted, magnified will be formed at infinity. Infinity. Okay. So we can also talk about, but let me give you this clue. There's only one for convex lens. There is only one condition where a virtual image can be formed. And marvelous, where must the object be placed under convex to form that virtual image? There's only one condition. What is that location or condition for us to get a virtual image for convex? Please, if you know, you can quickly contribute so we could move on. Though I've
When
called
the
back.
object is between the focus and the optical center.
Exactly. No, it's not the focus. Focal, principal focus, or the focal point. Okay. So
Sorry.
that is only on one condition, and you shouldn't forget this. Okay, you shouldn't forget this. That when you place the object between the center of curvature, the optical center, and then the principal focus, then a virtual image magnified upright will be formed. That's all. Okay. Apart from describing the nature of image from using ray diagram, we can also use... Hello.
Please, can you hear me now?
Yes, I can. All right. So we can also use the lens formula, similar to the mirror formula. It's the same, not even similar. Lens formula. We can also use the lens formula to describe the nature of the image form. And the lens formula is the same as when you have, okay, this is F, then this is C, 2F. When you place the objects in front, okay, I'm trying to create something just to explain so we could move on quickly. We shouldn't waste time on this because the same as what we've done for under mirrors. So when the object is placed in front, a ray parallel to the principal axis after refraction would have to pass through the second principal focus, a ray through the principal focus, the first principal focus after refraction would have to be parallel to it. So this is where the two refracted rays are meeting. And so an image, it isn't formed at F, but because I'm only using freehand, that is why it looks like that. Okay, don't forget, from here to this point is the focal length. From this point to this point is the object distance, U. From the lens to where the image is the image distance, V. Okay, and over here too, we can use the concept of, we can use equivalent triangles as we learned. Okay, triangle, this triangle, maybe OAB, and triangle, maybe if we name B, maybe CDE, equivalent triangles, to describe the nature of the to prove the length formula, which is still, we are not going to prove it because this is what something we've done and we are not going to waste time on it. Okay, okay, so triangle, we have this triangle here, we have this triangle over here, equivalent to this one, equivalent to this one. So this and this are equivalent. This one and this one are equivalent. Then this one, okay, and another triangle over here is also equivalent. And when we consider that, we can use that to prove the formula 1 on F is equal to 1 on U plus 1 on V. So the length, and this is the length formula, is the same as the mirror formula, where F is the focal length, U is the object distance, V is the image distance. Okay, establishing the relationship between the focal length, object distance, and then the image distance. Please, are we okay?
Yes.
So, and the lenses, this one also comes in. We use this vis-a-vis some conventions which we learned under mirrors. The RP convention, and the NC convention. Under the RP convention, anything real is considered positive. Anything real is considered positive. Under RP. Okay. Then anything virtual is considered negative. Okay, please, are we okay? So if you pick convex, a convex lens has a real principal focus, so its focal length is positive. A convex lens can form both virtual and real image. If the image is real, then V is positive. If the image is virtual, V is negative. Object is always real. Okay. Then, if you are looking at it for NC, the new Cartesian convention, only talks about the position of the object's image and then the focal length. So if it's a convex lens, the object is always in front, so object is always negative because this follows positive x-axis, negative x-axis, positive y-axis, and negative y-axis. So anything which is in front of the mirror is considered negative. So for convex lens, object distance is negative, focal length is negative. If the
Miss
image,
Elia,
hello,
please, any other, can you capture it?
I won't capture it.
Miss Elia.
But I'm recording. You let me capture it and then how many minutes do I have? Okay.
Hi.
Is that what? How many minutes? 5.
Yes, please.
So under the NC, anything in front of the lens falls within the negative x-axis. So negative. Anything behind is positive. Now, so for convex lens, U would be negative, F, okay, F would also be what? But over here, it depends on where the image, the object is. So if the object is here, then refracted rays will converge over there at the other end. So it's real. So it will be positive. So look at it. Okay. But the good news is also that for lenses, in most cases, we use RP in solving problems. Okay, because light will refract and converge here. Okay, if it's from this side, it will refract and converge here. If the image is real, it will be formed at the other side, positive. If the image is virtual, it will be formed at the same side as the object, negative. So that is how it is. So over here, do we use these conventions? Okay. Then magnification. Magnification, being it lateral magnification or transverse magnification. If it is lateral magnification, then M is equal to image distance over object distance. If it is transverse magnification, it is image height over object height. So the same value of magnification is also used. Don't forget, R is also equal to 2 times F. So we can make F the subject, okay, over here, which is R on 2, and then substitute it here to have this is R on 2, to have 2 on R. So this formula can be modified to 2 the same thing we've been doing under lenses, mirrors also plays out over here. Please, are we okay? Are we okay? All right. If you have any question,
Please, what does the M represent?
the what?
The
Magnification.
M.
Magnification. Okay. So we have, let's try a question. I think we have less than 2 minutes to wait for the 8-minute break. But before then, let me give you a question. I'm reading. Are you ready? A converging lens has a focal length. A converging lens has a focal length of 30 centimeters.
Miss Elia, are you giving us a question?
Yes. A convergent lens has a focal length of 30 centimeter, raised from a 2.0 centimeter, high filament that pass through the lens, raised from a 2.0 centimeter high filament that pass through the lens, form a virtual image at a distance of 50 centimeter from the